Welcome to the first video in Real Analysis. This first video is going to give an overview of the type of thinking that we're going to do in the first part of the course. In particular, we're going to look at a process for constructing number systems. So the basic idea is to use known number systems to construct new number systems. We're going to talk about that. We're going to outline a process of how we construct new number systems. And then we're going to apply that process to construct the integers from the natural numbers. Now in our class, we are going to be constructing the real numbers from the rational numbers. And what I mean by that is we're going to assume the rational numbers exist and that they have all the properties that we know rational numbers have. And then we're going to use those rational numbers to make real numbers that are not rational. But in general, here's how we construct number systems, or at least this is the process that we are going to use in our course. First, we want to develop an intuitive understanding of what the number system is like. These aren't directly applicable in proofs, but they're super helpful in constructing our number systems. We're going to make a list of axioms that precisely describes the number system. We're going to actually construct the numbers and define any operations, any relations that are needed to create the number system and satisfy the axioms that we created. And then finally, we're going to show that any number system that satisfies the axioms, even one that doesn't look like ours, is somehow equivalent to our construction. So I'm going to unpack these steps one by one. The first one is developing an intuitive understanding of what the numbers are like. It's extremely important in developing a number system. We're going to ask questions like, how do the numbers in the number system relate to each other? What kind of relations do we have on our number system? Are there any important operations that you can do to the numbers in your number system, especially if those operations are different from other existing number systems? Is there any way that you can develop any concrete conceptual models that can help you understand your number system? In making a list of axioms that precisely describes your number system, first you want to make sure the axiom list is complete. You want to make sure every axiom accurately describes what your number system is like. And just as importantly, we want to make sure that there are enough axioms that it distinguishes your number system from all the other number systems that currently exist. Your axiom list should not be redundant. It should not be possible to prove any of your axioms from any of the other axioms in the list that we make. And of course, your axioms should not contradict one another. Otherwise, you're going to have a number system that does not make any sense. Step 3, once you have the axioms that you want your number system to satisfy, you need to actually construct the numbers. Construct the actual numbers, define any operations on those numbers, any relations, anything that is needed to create your number system. You will, of course, want to use any pre-existing mathematical structures to construct numbers. In particular, you want to use any number systems that have already been constructed. In our case, when we construct the real numbers, we are going to be using the rational numbers. Any operations and relations, you must define those precisely. They must be completely unambiguous, what is called well-defined. You need to make sure that your definition satisfies all the axioms that you made in the previous step. And the last step is to show that any number system satisfying your axioms is somehow equivalent to our construction. Now, we need to make sure to define what it means for two constructions to be essentially the same. And what generally that's going to mean is the two constructions are exactly the same, except like the names of the numbers are different. They may look different, but they interact in the exact same way. And then once we have that definition of what it means for two constructions to be the same, prove that any two constructions that satisfy your axioms are also essentially the same. So what we're going to do here is kind of an abbreviated process of constructing the integers from the natural numbers. We're not going to go through the complete process. That would be a video that's way too long. It's going to be pretty long as it is. We want to sort of keep it down to a manageable level. But we're going to be constructing the integers from the natural numbers. So we're going to assume that our entire world of numbers consists of natural numbers. Those are the only numbers that exist in our world, and we're going to use those to construct integers. So first of all, remember, we want to develop some intuition. And one of the things about integers that's different from natural numbers is there's kind of two types of integers. There's integers that are positive and integers that are negative. The 5 is considered a positive number, and it has a corresponding negative 5 that goes along with it. And one model that can help us understand that dual nature of integers is a revenue cost model, right? So we think of integers as consisting of two types of natural numbers: revenue natural numbers and cost natural numbers. Now, revenue and cost are both natural numbers, right? If I owe you $5, that is a positive $5 that I owe you, but I think of that as a negative number in terms of money that I have, right? Revenue is going to represent the positive part of the integer, and the cost is going to represent the negative part of the integer. And what happens is if you combine revenue and cost, they can partially sometimes, or sometimes even completely, cancel each other out. So for instance, if you have a number that consists of 2 revenue and 3 costs, those interact with one another to give you 1 cost. We think of that as 2 revenue and 3 costs is one way of representing the number -1. One of the nice things about the revenue cost model for an integer is if you add 2 integers together that have their own revenue and cost parts, all you do is combine the revenue, combine the cost, and that becomes your new revenue and your new cost for your new integer. And if you multiply 2 integers together, we just have to make sure the result is consistent to how we understand how the properties of integers should work, using the commutative properties, associative properties, distributive properties, any other properties that we have for addition and multiplication. And we got to make sure to be able to define an order relation. One of the things that is true about integers, true about natural numbers as well, but certainly true about the integers, is we can put them in order. And the order relation that tells us that order is going to be less than. And the way that's going to work intuitively is smaller numbers have less net profit than larger numbers do. All right, so here's a list of our axioms for the integers. If you've had modern algebra, Math 350, these axioms will be very familiar to you. You've already seen them before. But these are the axioms for integers that we have that we need. So this is the axiom part of the development of integers. Of course, the integers have to include all natural numbers. Addition and multiplication has to satisfy all the properties that we know about addition and multiplication. First of all, they have to be the same for natural numbers as they were when natural numbers had no other integers. They have to be commutative, associative, and distributive properties for addition and multiplication have to hold. We have to have an additive identity 0. That's new, right? Natural numbers didn't have an additive identity. They started at 1. And we need a multiplicative identity. Anytime we have an integer, there needs to be an additive inverse. So if our integer is x, our additive inverse y has to satisfy x plus y equals 0. That's also going to be new. Has to have an order relation that satisfies 4 different axioms. And again, I believe you've seen these axioms before, but just in case you haven't, trichotomy is the fancy word for the first property. That means anytime you have 2 integers, either they're equal to each other, the first one's less than the second one, or the second one's less than the first one. Those are your only 3 possibilities if you have 2 integers. Transitive property has to be satisfied if you have A less than B and B less than C, then you have to have A less than C. Otherwise, there's no way that you can put these things in order. Next, you have to have something called translation invariance, and all that means is if you have A less than B, and if you add the same integer, we'll call it C, to both sides, then the inequality has to be the same. So if A is less than B, then that means A plus C is less than B plus C. We have something similar for multiplication. It's called scaling. If you have A is less than B, and if C is greater than 0, or 0 is less than C, so C is a positive number, if you multiply C by both sides, you keep the same inequality. So AC is less than BC. And finally, to distinguish the integers from some other number systems, like for instance the rational numbers, we have to have something called the well-ordering principle, and all that means is anytime you have a non-empty set of natural numbers, it has to have a least element. So in principle, when we finally construct our integers, we have to make sure that it satisfies all these axioms. Next, we want to actually construct the actual numbers, the actual integers. And the question is, how do we represent them? Well, again, remember, one of the ways that we've been thinking about integers is in this revenue cost model. Every integer has a revenue part, has a cost part, which then can be represented by ordered pairs. So the way we represent integers is going to be by the Cartesian product of the natural numbers with the natural numbers. So we're looking at ordered pairs of natural numbers. So the x-coordinate of every ordered pair is going to correspond to the revenue. The y-coordinate is going to correspond to the cost. So if that means every ordered pair represents the combined revenue and cost of the revenue part and the cost part. So for instance, if I have the ordered pair 2, 4, that means 2 is the revenue part, 4 is the cost part. That is going to represent the integer -2. That's 2 cost. And in general, AB, the ordered pair, is going to represent the integer A minus B, right? And again, this is intuition, right? We can't actually say A minus B is what it is because, again, if we had 2, 4, 2 minus 4 doesn't exist in the natural numbers. Again, our whole world is the natural numbers right now. Now, one of the disadvantages of representing integers this way is that every integer can be represented by many ordered pairs. In fact, infinitely many ordered pairs. For instance, the number 4 is represented by the ordered pair 9, 5 and 6, 2, right? 9 minus 5 is 4, 6 minus 2 is also 4, among many other, infinitely many other ordered pairs represent the number 4. Which means we have a little bit redundancy in our representation of our numbers. We'll find a way to figure that out. The way we're going to do it is we first of all need a rule that tells us when two ordered pairs represent the same integer so we can collect them all together in an equivalence class. So we're going to use our intuitive understanding of ordered pairs in order to tell us when this happens. Remember, we're thinking of the ordered pair AB as the number A minus B. We're thinking of the ordered pair CD as C minus D. So if we want to know if A, B, and C, D represent the same number, well, this is what we really want. We want A minus B to equal C minus D. Now that is not a good natural number equation because it has subtraction. Subtraction is not a good natural number operation. But if we add B and D to both sides, we get A plus D equals B plus C. That is a good natural number equation. It has addition, which is valid no matter what natural numbers A, B, C, and D that you have. So our rule for AB being related to CD is precisely when A plus D is equal to B plus C. Now, after this, we need to prove that this relation is an equivalence relation. You've seen this in Math 210. Presumably, you've seen it maybe in Math 315 or Math 350. You have to prove that it is reflexive, symmetric, and transitive. We're not going to do that here, but you could do that if you wanted to. And then we're going to find the integers to be the set of all equivalence classes of that equivalence relation. So each of those equivalence classes represents a number. All those equivalence classes together form all the numbers in the integers. So that's the construction phase of the integers. We've actually made the integers. Now, of course, the integers aren't going to be very meaningful without, say, binary operations. We got to be able to do some arithmetic with them. So what we do with addition is, remember, our revenue cost model says combine the revenue, that becomes our new revenue. Combine the cost, that becomes our new cost. So if I'm taking the equivalence class of AB and adding that to the equivalence class of CD, I'm going to combine the cost, A plus C, or combine the revenue, A plus C, that's going to be our new revenue. Combine the cost, B plus D, that's going to be our new cost. And then our result is the equivalence class of A plus C and B plus D. Multiplication, a little more complicated, but we're going to use our understanding of what these ordered pairs mean. If I want to multiply the equivalence class of AB with the equivalence class of CD, again, intuitively, I'm multiplying A minus B times C minus D. And if I work out the multiplication and combine the terms in a convenient way, I get AC plus BD, which is a positive natural number, minus AD plus BC. AD plus BC is a positive natural number as well. But I'm subtracting it, so that is going to be the cost part of my integer. So my definition is going to be the equivalence class of AB times the equivalence class of CD is the equivalence class of AC plus BD, AD plus BC. Now we have to figure out the order relation, but that's not going to be too bad either. We want to put the integers in order with the relation less than. So the question, of course, is when do we have the equivalence class of AB less than the equivalence class of CD? And again, we're thinking about AB being A minus B, CD being C minus D. So we're really asking our question intuitively, when is A minus B less than C minus D? And can we put this in a way that is friendly toward natural numbers? Once again, we're going to use translation invariance, add B and D to both sides. We get A plus D is less than B plus C. That's our test. So we have the equivalence class of AB less than the equivalence class of CD precisely when A plus D is less than B plus C. All right, so again, I'm not going to do all the details, but I will tell you about the work that's left to do. Right. First thing we have to do is, you might have noticed that I was kind of playing a little bit fast and loose with the definition of addition and multiplication and the less than relation. There was a little bit of ambiguity in there that was hidden. We do have to prove that those are all well defined. I'm not going to do that here, but you could do that if you wanted to. We then have to prove that our construction, along with all the operations and the less than relation, they satisfy all the axioms. And then we have to prove that our construction is unique up to relabeling the elements. Again, that's beyond the scope of what we're going to do here. We are going to go through all those details with the real numbers, right? That's going to take several weeks, right? But I'm going to leave out the details for the integers. If you want to talk to me about those, you can talk to me after class. You can talk to me during office hours. I'm happy to talk to you about them, but it's kind of beyond the scope of this video. Anyway, the next video we'll start talking a little bit about what some of the irrational numbers are going to look like.